So without further ado, I'd like to introduce our speaker, Kenneth Billingham. He is the International Product Specialist for KEG GmbH, KEG Technologies Incorporated. It's a German manufacturer of highly efficient pipe cleaning tools. His responsibilities include customer and reselling support for all of Canada, Australia, New Zealand, as well as the Western US. The many years of experience, as well as a diverse knowledge of the many different collection systems throughout his area of responsibility, are instrumental in helping him find solutions for the many challenges his customers regularly face. He was born in Calgary, Alberta, and raised in Quebec, and currently lives in Abbotsford with his wife, Judy. Welcome, Kenneth.
Thank you. Thank you, Anna. I appreciate that. I guess I'm live on the speaker. Thanks, folks, for attending. As Anna said, my name is Ken Billingham, and the presentation today is the science of pipe cleaning. We're going to go through a lot of different things. We're going to look at some novel ideas. We're going to talk about some basics about jetting and how jetters work and how the flows and pressures combine to make cleaning power and things like that. As I understand it, the ability is there for you to ask questions online, and I will get those questions and I can respond to them either at the end or I can respond to them as they come up if they're appropriate, if we're dealing with the subject that needs to be talked about. So as we go into this, again, if you'll be patient with me, we'll go through some basics in the beginning and see where we're off to. So that's the slide forward. All right, off we go. So what we're going to talk about today, we're going to talk to the crews who are out there cleaning the lines. We can show you ways or bring you ways to do a better job, to be able to work smarter and become cleaner, healthier aspect to the way jobs are done, maybe a safer job. If you're a manager running a department or trying to make things work with limited budgets or limited manpower, again, I can show you or we can talk today about ways to help meet the request or the demands of the job with a little less equipment, maybe a little understaffed, and making things happen that way. And if you're a business owner, I mean, if you're in business, the only reason you're in business is to make a profit, or one of the major reasons you're in business to make a profit. And there are points we're going to talk about today that will show you and help you to see and be able to make a more profitable venture when you're doing these tasks and jobs for cities. If you're looking for solutions for your questions, I hope to be able to provide some for you later on. And I'm going to be talking to you about the design of nozzles and how to apply these designs to make them work to your best advantage. Some of the benefits of going to a Tier 3 nozzle or a better quality nozzle, more efficient nozzle, is of course you clean your wastewater and storm lines better and quicker. You're going to be looking at fuel savings anywhere between 9 and 17% of a fuel savings in the jetting or pipe cleaning process. Your man hours, machine hours to do a specific task or job will drop. Your wear and tear on your equipment will be reduced, and you will conserve water, which is quite often a big issue for a lot of folks because of the cost of the water, as well as adding that extra water to the wastewater plant. Sometimes that becomes an issue for them. And of course, costs. It's all about cost. How do I get this system in my municipality and my utilities and responsible for? How do I get that job done with the lowest possible denominator for costs? And then last but not least, of course, there's our job is to clean pipes. Point blank, no other question about it. What we're here for is to clean pipes and get it done as quickly as possible. But before we get into this, I need to take a few minutes and visit back to basics. So I'm going to take us back to a point that maybe even a lot of you folks already understand, but not everybody does thoroughly, or there's been some misinformation, so I'm going to try and straighten some things out, put some facts clear in front of everybody's mind, so when I proceed with the rest of the presentation, you'll see what's going on. So what we're going to talk about today, we're going to talk about the water pump, we're going to talk about the hose reel and the hoses that are on there, we'll talk about the water pressure gauge and how that has an impact on what things are going on, and last but not least, we'll talk about nozzles. And in the second part of the presentation, we'll talk about the way we clean pipes and what's the best route to do things and what can make a difference. When we talk about pumps, I don't speak about a specific manufacturer or brand or style of pump. I call a pump a positive displacement volumetric water pump. Basically, if it moves water, supplies the flow I need, can sustain the pressure that is required to clean the pipes, it's sufficient for me and I can work with it. Many different manufacturers, they will all tout their product and say mine's better than his and his is better than mine, or vice versa. But at the end of the day, from my point of view, as long as the pump supplies water and can maintain the pressure in the system, we're good to go. If the pump does not create, you've got to remember this too, the pump is not what creates the pressure. You know, I use the terminology sustain or maintain pressure. The pump provides flow. The pressure comes from the restrictions, i.e. the nozzle in the line. So the nozzle and the way the nozzle is set up will directly affect how efficiently, how well, and how much energy your truck requires to get a job done. And the main purpose of this pump is to transform the mechanical energy in the vehicle that you're driving, or the trailer or whatever jetter you have, and turn it into hydraulic energy, because we're cleaning with hydraulic energy. We talk about hose reels and hoses, and we can discuss at length how much hose is appropriate to have on a truck. What size hose do I want? Do I want 3/4 inch or 1 inch? Do I need 1 1/4 for certain jobs? Is a 1/2 inch hose able to do specific tasks for me and everything else? All questions that I field on a regular basis, and they're all valid. There's no black and white. There's a lot of gray zones in this, and we can set and look at those. The diameters and lengths of hose to choose from have a huge effect on how your jetter or your cleaner is going to work. The main purpose of this hose is to transmit that energy that we have now, that hydraulic energy we have at the truck, and to deliver it to the job site, which could be 20 feet away from the truck, or it could be 200 feet, or it could be as much as 600 or 700 feet away from the truck where you need to do the work and clean the pipes. Chart I have in front of us here now, this chart looks at the different sizes of hoses. You can see on the left-hand side, 1/2 inch, 3/4, 1 inch, and so on. I've highlighted the 1 inch hose because that is the most common in industry, and that is the one that a lot of municipalities and even contractors use to do most of their cleaning. So we're going to stay with a 1 inch hose for examples, but we can discuss if somebody wants to 3/4 inch or a different size hoses if that's what their need is. If you look on here, you'll see the 1 inch hose typically has a working pressure up to 3,000 psi, and the flows it's designed to handle is between 30 and 80 gallons a minute. It doesn't mean you can't do outside of those parameters, but it's not where the hose is most efficient to be used. And you look on this chart, you'll see right beside the GPM, 30 GPM, you see in brackets there's a number there, 0.16, and in the 80 gallon a minute there's another bracket that says 1.1. This is the loss of pressure per foot of hose, all based on the flow that's there. So if I have a 1 inch hose that I'm using and I'm pushing 80 gallons a minute through that hose, I lose 1.1 pound of pressure per foot of hose, and over a 600 foot length of hose I can expect to lose between 660 and 675 psi, which will have an effect on how well we can clean and what I need to do with the truck to make things happen. Conversely, if I lower the flow down to 30, or even let's take it down to 50 gallons, a more common size for the 1 inch hose, or flow for 1 inch hose, if I take the flow down to 1 inch, then I lose the equivalent of 1/2 a pound of pressure per foot of hose. So I've gone from 1.1 down to 0.5, or 1 pound of pressure per 2 feet of hose. I've cut the pressure loss in half, and I've also reduced my flow, which has a lot of additional benefits. Just to reiterate, in the hose, as we take the pressure up and raise the flow, the end pressure at the end of the hose will drop down because of the resistance and the pressure loss over the length of the hose. Conversely, if I can lower the flow, my pressure will rise at the end of the hose. And if I look at the next statement on this slide, it says that pressure cleans the pipe. Pressure is what's going to take the material off the walls. Pressure is what's going to propel the nozzle up the line, along with flow, but it's more important that pressure is there. Flow is there to help carry material away. If you're working in a sanitary sewer system, it's typically a gravity-fed system or gravity-operated system. So if you can loosen the material that's causing the problems and add a little extra water, it should be sufficient to bring that material back to the truck or bring it down to the water treatment plant. And the whole idea is to do this as efficiently as possible. So again, pressure will clean, flow will move material. When I look at the water pressure gauge, I want to remind folks, this water pressure gauge that you're looking at will indicate the pressure at the truck. where the operator is standing. Some 500 or 600 feet of hose later, the pressure loss is going to drop. We saw that in the previous slides, and we're looking at it again here. So the pressure gauge is a tool for the operator to set his truck and work within parameters, but he has to understand that you are not working the pressure at the end of the nozzle. There are a couple of questions. Last name, Ken Green. Ken, yes, the presentations are available. I believe the association will make them available, and I will make it available to them should it be necessary. Would you be able to send handouts so I can take notes? Again, presentations are available. We can send them along. In wastewater cleaning, no, this is wastewater cleaning, sir, and that's a Mr. Hogan, or Chris Hogan. The question is just wastewater cleaning. It is sewer wastewater cleaning, stormwater cleaning, any pipe cleaning process you're going to have, these basics will apply to. So again, the water pressure gauge is there to provide information to the operator so that he can make some operational decisions. I want to look at some comparisons and go over what I just said about pressure loss, 1.1 pound per foot, and so on and so forth, and put it into real life for folks. So here I have, you notice I say nozzle jetted at 80 GPM. So I've jetted the nozzle to give me 80 GPM. I'm not considering what the truck is capable of doing. As long as it can provide the 80 GPM, I've got it. So at 80 GPM, 2,000 PSI with 600 feet of 1-inch hose, a very common setup, a very common configuration. The pressure loss at the end of the hose is, or the pressure at the end of the hose is 1,327 PSI. A loss of 672 PSI, or 34% of what I started with. You notice I've got in brackets, it's 1.12 PSI per foot. My number from before, 1.1, this is 1.12. What I want to look at here and point out is the available 62 FHP. FHP is fluid horsepower, and it's an engineering term to let you know how much energy you have available, how much power you have available at the end of the hose to put to work. So this is just what's being delivered to the end of the hose after the water is run down the length of the hose and go from there. This FHP is important to what I'm going to talk about later, so I'm going to talk about this for a second. The formula for finding fluid horsepower is on the screen as well, and you'll find all these formulas I use all the way down are there. They're used in industry, they're used by engineers. Flow times pressure divided by 1714. I have no idea what 1714 is for, but all I know is that's the formula they use. Okay, so again, fluid horsepower lets me know how much power I have available at the end of the hose, just where I'm starting to get ready to go to work. Same setup, but I've changed the nozzle from an 80 gallon a minute nozzle to a 60 gallon a minute nozzle. I've dropped the flow. I've still got 2,000 PSI. I've still got 600 feet of 1-inch hose. And my pressure at the end of the nozzle is 1,621, or at the end of the hose is 1,621 PSI versus 1,372 we had before. A loss of 294, or 22%, I'm sorry, a gain of 294 and 22% more pressure available, and I've diminished my flow by 20 gallons. Again, you see the pressure loss in yellow there at 0.63 PSI per foot. This is, again, I'm reducing my pressure loss and I'm maintaining or retaining my pressure at the end of the hose, which is where I want it to be so that I can clean and propel the nozzle as I need it to be. I want you to compare the available FHP of 57 at 60 gallons a minute to what we had before at 80, which was 62 FHP. Not a big difference in power availability, but quite a bit of a difference in the way the water is consumed on the truck. Take the same nozzle, but I'm jetting it at 50 gallons a minute now, so I've just changed things around. I've made the nozzle a 50. I've knocked it down a little bit. My pressure at the end of the hose goes up to 1737. My loss is only 13%, or 0.43 per linear foot. And I've got a fluid horsepower FHP of 51. So again, I'm still staying in that 50-60 range with the fluid horsepower, but I've reduced my flow dramatically. And some of the other benefits of reducing flow is that you're going to reduce the demand on the truck, the engine, the fuel consumption, the water pump, and all those things. All that truck that works hard and is costly to maintain and operate, I can help you reduce those costs and keep the truck on the road and working if we can just take the flow down and go from there. This is a 3/4 inch nozzle comparison. If you see what's happened on the 1-inch nozzle, I had a pressure loss in yellow of 0.43, And on the 3/4 inch nozzle, because it's a smaller diameter and I'm pushing the same volume of water through, I lose 1.82 psi per foot. So by doing that, what ends up happening is I either have to take the pressure up higher at the truck to keep a pressure at the end, or I have to find a way to reduce that flow to bring it down. And again, if I take things to extremes, here's a 35 gallon a minute setup running on a 1-inch hose again, and my pressure loss is only 0.21. So the whole concept here of what I'm trying to bring across is that the lower the flow, the higher the pressure at the end of the hose. And if pressure is truly what propels and cleans, then I can propel and clean a lot better with these combinations than I can with others. But the trick is having nozzles that can convert that energy at the end of the hose into something I can work with. On this chart here, I've done a lot of information, and we can go over it as such. On the left-hand column under GPM, you see the numbers 80, 60, and 50. Then you see engine at 104, 70, and 65. What that relates to, at 80 gallons a minute, you need 104 horsepower from the engine to drive an 80 gallon a minute pump. Okay? It might vary slightly from manufacturer to manufacturer, but the truth is still there. The fact still remains. I use Myers Pumps numbers for these. So again, Myers is a well-known, well-recognized company, but the information there is valid across the whole field. But what I'm showing you here is at 80 gallons a minute, I need 104 horsepower. At 60 gallons a minute, I need 70. And at 50 gallons a minute, I need 65 horsepower. So at 50 gallons a minute, I need 42% of the power, or sorry, I drop the power demand by 42% to make the 50 gallons a minute I need to do the job I want to do with. I also want to underline at this time, too, is if you think about things, and everybody is familiar with a Vactor truck. Vactor uses a single piston design pump that runs back and forth in cycles, and that pump pushes 5.5 gallons of water every time it goes out and comes back. And if I'm pushing 80 gallons a minute out the hose, that pump needs to run or cycle 15 times in a minute to give me 80 gallons a minute. But if I run 50 gallons a minute, it needs to cycle 9 times. At the end of X number of years of life or hours of operation, everything else, it adds up to a lot of cycles, which means that your life on the pump and your wear and tear, your repairs is going to be much better. You see the fluid horsepower ratings are there in the third column, and then you can see on the under 1,000 gallons, what that is just showing you how long 1,000 gallons will last. At 80 gallons a minute, you burn it up in 12.5 minutes. At 50 gallons a minute, you get 20 minutes worth of jetting time. So I have more time available to clean and be in the pipe. So what I'm showing you here, basically, a couple of really nice cars, but the whole concept of this is I've got all this power. I've got all this energy that I can use. And if I don't put it to work properly, if I can't get that power to where it needs to be, in this case, the back tires of the car, I'm not going to win races. I'm not going to do anything with it other than have a very good-looking car. So if I do the same thing in the concept with working with jetters and nozzles, is if I have all that power and my jetter's delivered and is given everything I paid to have and it's there and my crews are out there and they're doing their job, but I don't have a tool on the end of the hose that's going to return that power back to cleaning efficiencies and propulsion and things, then basically I'm wasting a lot of that energy. What we're going to talk about now, finally, the fellow who sells nozzles, is to talk about nozzles. So again, I write up, going back to basics of water systems, talk about nozzles. I write nozzles and I use an S with a dollar sign as opposed to the S itself. And I do that on purpose. And it's got nothing to do with the fact that I earn my living selling nozzles and doing this kind of work. What I'm trying to explain here, what I'm showing folks here, is that if you use the right tool, you buy the right nozzle, you use it correctly, your cost will drop. Your performance, your productivity will go up. So again, the nozzle redirects the flow of water. To the point we've come to now, we've delivered water to the truck. The pump has done its job. It's put it in a hose and sent it down the line. It's traveled 600 or whatever number of feet you have on the hose, and it's waiting to go to work. The nozzle will pull the sewer hose up the line. It will take the material and move it back towards the truck if that's the design you have. The selection and application of the nozzle, so in other words, choose the right tool and use the tool as it's designed, and you will find that your performances will go up quite a bit. Everybody here is probably familiar with NASCO, who is the National Association of Sewer Servicing Companies. It's a American or North American association that represents utilities or cities. It represents contractors and people who do this for a living, and it represents people like myself who are vendors or providers of product to the industry. To be able to meet, we talk about a lot of different things. We put in place a lot of regulations. NASCO has something they call the Jetter Code of Practice, and there are other things. Everybody knows NASCO as well. If you've done CCTV camera work and your camera guys are PACP certified, that's all NASCO. So what NASCO has done is they've gone and taken this nozzle design and nozzle manufacturing and the way nozzles work and kind of categorized them into 3 separate groupings. The groupings are, of course, a Tier 1, Tier 2, and Tier 3. Tier 1 being the least efficient, Tier 3 being the most efficient. We're currently working, or NASCO is currently working to improve this Jetter Code of Practice manual they have, and they're looking at this whole setup and making some changes. And we might well see like a Tier 4 come in, because there have been some advances in nozzle design that don't quite get covered by the Tier 3. When we look at nozzle design, we look at the way the water is turned around inside the nozzle. I'm not going to talk about angles of jets and stuff like that at this time. We'll talk about that in a little bit. But right now I want to address how the water is redirected inside the nozzle. And this is what makes a huge difference between a Tier 1, a Tier 2, and a Tier 3. And even some manufacturers, there's a huge difference in the way things are done. So to reiterate, Tier 1 and Tier 2 nozzles. Tier 1 are the least efficient nozzles on the industry. They're also the least expensive to buy. They're the, well, I like to call them the most expensive to operate, because you really got to put the power to them to make them do what you need to do and go from there. Tier 1 nozzles and Tier 2 nozzles are built identically inside. They are a flat bottom. So if you think about the water coming down the hose and entering into the nozzle, and when it gets into the nozzle, there's a flat or a wall there, and that water just slams into that wall and literally stops. And the next bit of water coming down the hose pushes that out. It creates a fair bit of turbulence in the nozzle, and turbulence is loss of energy. And it creates inefficiencies in the nozzle as well, and likely excessive wear or premature wear should the nozzle not be designed adequately. In a Tier 3 nozzle, the biggest thing about a Tier 3 nozzle is if you look inside the nozzle, you can see how the water is directed around a curvature. So the water, rather than slamming into a wall or hitting a hard angle, is coming into and hitting a curve and going around that curve and coming back out. So you basically take the energy entering into the nozzle at the end of the hose, the FHP we talked about before, fluid horsepower we talked about before, and redirect it in a more efficient manner, which means I'm applying that energy to the walls of the pipe, to the cleaning, to the propulsion factors, and everything else. And this makes a big difference. In Tier 3 designs, each manufacturer has their way of doing it, and some of them do an excellent job, and some of them do a pretty good job, and some of them don't do a very good job at all. And it needs to be determined by the end user or the customer buying the nozzle, what product do I want? What price point do I want to pay? What performance do I need out of this nozzle? What's my expectations of getting this job done? So when I look at tiers, I look at Tier 1 nozzles, and on the left-hand side you have a picture of a Tier 1 nozzle. Really simple design. If you pick it up and look at it, the easiest way to tell a Tier 1 nozzle, if you look at the orifices the water comes out of, if those orifices are drilled and not a threaded or replaceable jet, that's a Tier 1. And the biggest thing to say about a Tier 1 nozzle is, number one, it's cheap to buy. Under a couple of $100 to buy a nozzle, and a lot of guys think that's just exactly what they need. But the problem with a Tier 1 nozzle is it's 30% efficient. So that fluid horsepower we had at the end of the nozzle, or the end of the hose, that fluid horsepower, let's take the 80 gallon a minute example of 62, 30% of it gets put to work and 70% of it gets discarded. So when I talk about this nozzle and I call it the most expensive to operate, that's what I'm referring to. The acquisition of the nozzle is cheap. Using the nozzle over time can be very expensive, as well as the fact that they don't necessarily last that long. So a 30% efficient nozzle discards 70% of the energy that we want to use. A Tier 2 nozzle, remember, is designed with the exact same flat, straight surface inside of it, but where the difference is the Tier 2 nozzle has replaceable nozzles and jets, or inserts. So when we get to this level, we basically double the efficiencies, bringing the efficiencies of the nozzle up into the 60% range. And by doing that, by changing the orifices and putting in those replaceable orifices, we are able to, A, renew the nozzle when it gets worn down, but more importantly, I can tune that nozzle to the job you need. So if you needed a nozzle set up for 60 gallons a minute and you needed it for a specific task, we can set that nozzle up and go that route. Again, you double your efficiencies, which means that you're going to theoretically double your output when it comes to the nozzle. When we talk about a Tier 3 nozzle, remember I described that as being a nozzle with a manner inside the nozzle to turn the water around. And again, different manufacturers have different approaches, and I invite you to experience, try them, see them, talk to the manufacturers, take nozzles on a trial basis, and see what they can actually do. When you look at Tier 3 nozzles, the requirement for Tier 3 nozzle is there must be some way the water is turned around inside the nozzle. So that's that redirection of water through a smoother curvature. There must be replaceable inserts. So again, we get that efficiency of the inserts coming in. But more importantly, to meet a Tier 3 level, a nozzle must be a minimum of 80% efficient. So if you have 83, 84, 85% efficient nozzles, you meet that requirement, and that is a Tier 3 nozzle. There are nozzles out there that certain manufacturers make. We are one of them. There are 2 others out there that I know of. And we make nozzles in the high 90% efficiencies. So when you think about this for a second, I can opt for a 30% efficient nozzle, or I can go for one that's closing in on 100%. The energy that I'm paying for, the truck that I'm delivering to the job site, the fuel, the maintenance cost, all of that stuff that's involved, I can use that energy delivered by that truck more efficiently, which means I can A, get more done, or B, use a lot less energy and mechanical power to get it done. The whole concept of this Tier 3 and the high efficiencies is the premise of what we're talking of today. When I look at this chart here, this chart looks at a few different designs of Tier 3 nozzles. On the left-hand side is it's our design, and it is a very efficient design. There are a couple of different competitive designs in the second and third pictures. And if you look at that, you can see the swirling inside the nozzle. What's happening there, that's inefficiencies showing up, and it's causing the energy to drop. Again, Tier 3 nozzle, as long as it meets an 80% threshold, is a Tier 3, and it's a good nozzle, but you can get better than that if you should decide that's where you want to go. Along with the nozzle and the way the water is turned inside, the insert and the way it is manufactured has a huge effect. Yes, you can get everything from a steel insert with a drilled hole. You can get carbides, you can get sapphire, you can get all kinds of materials in the inserts to make things work. But more importantly than what the insert is made from is the shape of the insert. If you look at these photographs, on the left-hand side you have an insert this is a titanium ceramic insert with a pathway or a funnel effect that comes down and doesn't have much of a barrel into it. If you look at the design, the water gets compressed down to the size of the orifice we want, and once the water goes through that orifice, it wants to expand and go back to its natural state and come back out and cause a misting or a spraying kind of an effect. On the right-hand picture, you'll see a nozzle that's got a longer barrel to it. So the idea here is we force the water into the size we want. We maintain it for a longer period of time in that size. So when the water comes out of the nozzle, it actually follows that path and stays in that tighter pattern longer. More direct, a stronger, more concise water jet will give me more thrust, more power. We're using less pressure, water, and all those good things. If I look at this nozzle design here, basically what I've done is highlighted. I've highlighted with the big red arrow on the left here that the design, the way the water is turned, and if I look at the other side, it's the insert that goes into it. So it's an engineering, or it's an engineered design to work together, and the most efficiency you're going to get will be with something that's working and designed to work together to give me the higher efficiencies. This is going to be a video, if it plays properly, it's going to be a video. It's not going to play. Where's my AV guy? Can we get that video to play? Oh, you know what? That's a PDF you have. Yeah, it's not going to play. Right. Gotcha. I knew there was a reason for that. Okay, well, technical difficulties aside, I'll explain to you what this slide was designed to do. What this was meant to show was on the left-hand side is a 98% efficient nozzle, and on the right-hand side is an 84, 85% efficient nozzle. Both good nozzles, both able to do the work we want them to do. But as you can see, as we start the pressure up, we start putting water into the design, the jet of water coming out of the nozzle is very compact and very straight. But as I apply more and more pressure to the nozzles to this test bench, you'll see that the jets on the right-hand nozzle, and you won't see the video unfortunately, but the jets on the right-hand nozzle will start to fan and open up. And what happens then when I open up those jets and sprays, I lose the ability to thrust and power out of that. When the water jet stays tight together and concentrated, then that gives me more push and thrust. If that tight jet of water hits a rock or a brick or some obstacle in the pipe, it's going to have an effect. It's going to send it on its way. It's going to peel it off the wall. It's going to do what has to happen to it. So again, the efficiency of the nozzle is seen very clearly in the design of, or the way the water comes out of the back of the nozzle. And that's one way to identify too. If you're looking at nozzles and you're trying different brands out, or you've got a nozzle and you're not sure of, if you can see it operate in a clear tube or whatever, you will be able to look at it and say, okay, that's got a very tight water pattern, this one has less, and you can determine amongst your own nozzles or anything you're considering buying which is the best choice for us. We go back to my chart here. We're going to look at the 80 gallons a minute, the 60, all that flow down the left-hand side, and the engine horsepower required. Under the heading of hose, I have the fluid horsepower rating, so you see 62, 57, and such. And if I look at a Tier 1 nozzle, remember Tier 1 is a 30% efficient nozzle. If I look at a Tier 1 nozzle, I have a 30% use of 62, gives me roughly an 18 fluid horsepower that is actually put to work. And conversely, if I drop it down to 50, I've got 15 fluid horsepower that is put to work. But that being said, that means there's, well, if the fluid horsepower 15, there's 36 fluid horsepower at 50 gallons a minute that I'm discarding, I don't need. I take a Tier 2 nozzle. Now I basically doubled the efficiency of the nozzle by having replaceable inserts in the nozzle. And if I double the efficiency, then the output of the nozzle will double accordingly. And as you can see on the chart, I've gone on the 80 gallons a minute from 18 to 37 and on down the road. So you can, in theory, if you were running a Tier 2 nozzle, you could run less flow, less pressure out the nozzle and still have the same cleaning power as a higher flow and pressure nozzle. Tier 3 nozzles, remember, we're using an assumption here in Tier 3 of 80% efficiency. This meets the threshold of the efficiency levels. And if you look at that and look at the 50 gallon a minute reading on the Tier 3 nozzle, it reads 41. That surpasses a Tier 2 nozzle at 80 gallons a minute. And I've got the savings of 30 gallons a minute of water and all the other things that go along with it. I made a comment earlier about 98% efficient nozzles, and there are manufacturers who do make these nozzles. They are out there. They aren't going to be your least expensive nozzles, but some days they can be the tool you really need to have because it gets the job done. If you look at the output, and again, I'm going to go back to my 50 gallons a minute. A 50 gallon a minute Tier 3 98% efficient nozzle gives me an output of 50 fluid horsepower at the end of the hose or where the nozzle is, as compared to an 80 gallon a minute Tier 3 that just meets the requirement, just meets the threshold. So I can run a high efficiency Tier 3 nozzle at 50 gallons a minute and perform, clean, propel just like an 80 gallon a minute Tier 3 nozzle that is just meeting the minimum of what we need. Okay, and conversely, if I raise the flow up, my power goes up. So if I have lines that are excessively dirty, or I have lines with a good hill to climb, or I have other issues like that in the line, like grease stuck to the sides, and I want to deliver an impact to that obstacle and move it out of the pipe and get it moving down towards the treatment plant or back to my truck, I can do that better with a higher efficiency nozzle than I can with the others. If I'm running a Tier 2 nozzle in a similar application, I've got to power that truck to its maximum. I've got to go at maximum flow, maximum pressure, and try and pull what I can off the walls. And I've had many, many instances where I've had guys who've gone out, worked with tools, and I'll show up on either a demonstration or a sales call with a rep, and we'll look at things, and I'll ask them to go back to a job they've done recently in the last few days. And maybe they had a little bit of difficulty with, and I've gone back, and the line is clean because the guy spent a half a day here, and he ran, I don't forget how many tanks of water through this pipe, and I'll go in with a high efficiency nozzle and bring more material back. And it blows people's minds. They say, but it had to be clean, and we were here for 4 hours. Well, yeah, you were there for 4 hours, and you did all the work you were required to do, but the tool you had wasn't as sharp or as efficient as you needed, and it didn't supply you what you needed. So what I'm showing you here is that with a better efficient nozzle, I can get those jobs done quicker and a little bit better than with a nozzle delivering less power. So let's look at the benefits. If I leave the truck at the same output, so I'm running my truck, I like to run an 80-gallon-a-minute truck, I'm just using this example, and I have an 80-gallon-a-minute truck, and I like to run it at 2,000 psi, and I have 600 feet of 1-inch hose on the truck, I can expect with a Tier 3 nozzle to have more pulling and cleaning power, but more importantly, I have over 3 times the power of a Tier 1 nozzle at that same flow and pressure. And a Tier 2 nozzle, because it's twice as efficient, okay, I'm going to cut that difference down by half, so I go to 1.5 times more power out of the nozzles. Now, we'll talk in a minute about where this makes the savings for you. We're going to go over that shortly, but before we get into that, this is one of the important things I want to look at. If I keep the truck at the same input, I have more out of the nozzle. But if I was happy with the output from the nozzle, my cleaning power and everything prior, I can run the vehicle or my jetter at lower flows, at lower pressures, and deliver the same cleaning power that was satisfactory before. And if I can do that, one of the biggest advantages I have is I can drop the engine RPM down, I can drop the water consumption down, the wear and tear on the vehicle comes down, all that stuff starts to take effect. And if the water tank lasts longer, as we saw before, 12.5 minutes to 20 minutes, 80 to 50 gallons for 1,000 gallons, if the water lasts longer, that means I can stay in the hole longer. That means I can clean more linear feet of pipe with this tank of water on my truck than I can using a different combination, using a different setup. So if I can clean more, that means I have to go less often to refill. If I go less often to refill, that means at the end of the day, I've managed to spend more time, more minutes, hours in the pipe cleaning than I have running around chasing water. Some of the advantages, of course, maintain cleaning and pulling power, and again, the satisfactory level. Water consumption, fuel consumption, wear and tear all drop. Noise and heat levels go down. We're getting into the cooler months. Heat, kind of not a bad thing in January. But in August, maybe not quite so much. Okay, so we can do that as well. And again, noise, by reducing noise and stuff in the operator's area, it helps a lot. And it increases productivity because, again, I can spend more time in the pipe. I've shown examples. I've run tests head-to-head. My own products on 2 identical jetters. I'm thinking of an example in Montreal. And we ran head-to-head. And at the end of the day, using our products, properly applied, the right methodology for cleaning pipes, I actually I increased the productivity by 20%. So I did 20% more meters at the end of the day than the other truck. And I used 20 liters less fuel. Okay? At the end of the day, if you're running a fleet of trucks, or at the end of the year, that's a lot of money. So the benefits of reducing flow, of course, water consumption goes down. I fill up less often. The crews have more time in the pipe running than they have chasing water. And the other thing you think about too is how many times do you work a line and you're out of water and you got to go get more water and come back to the same line, set up again and run and finish this section. If I can get more done with the tank of water, then I can, when I set up, get it done and move on to the next section and go from there. I have more pressure to clean. Remember I showed how if the flow drops based on the size and diameter of the hose, if I drop the flow down, my pressure at the end of the hose will increase. And if my pressure at the end of the hose will increase, that means I have more thrust, means I have more cleaning power, more stuff to peel the grease and whatever off the walls of the pipe. My fuel savings are there. I can run, and I've done it, I just did it just last week here at the City of Richmond, run a truck at idle. Okay, and we cleaned and I believe it was an 18-inch pipe with a fair bit of debris and soil into it, and we got it done in one pass. And the guys were amazed at how well this could work. They just shook their head and said, I don't believe we just did that. But again, it's the same thing. It's all stuff, take it, put it to the test, have a trial. Maintenance costs go down. Your environment, your safety environment goes up, guys. If your noise levels have gone down, automatically your safety levels are down because you still need hearing protection, but it's not as bad. More importantly is if the noise levels are down, you're more aware of the area around you, your work area. So if there's a car that honks a horn or a workmate that yells, hey, watch out, you'll hear that and you'll see what's going on and you have a better chance to get out of harm's way. Heat, as I mentioned before, it's great in the winter, but not so good in the summer. Some of my travels take me into some very warm climates, and believe me, staying away from heat is very, very important. 44 degrees and 45 degrees in Australia was harsh. Okay, SSOs, and typically when I talk about SSOs, there's always a few people in the room that go, oh yeah, the room here is empty today, folks, so I'm assuming that we all know what an SSO is, which is a sanitary sewer overflow. That's basically when that stuff runs down the street and people are getting upset with you and you got to go and get this dealt with. If you can get around to your system and do a better job cleaning, A, do a better job, and B, do more in a year or in a month or in a quarter or whatever you're doing, and get around your system a little quicker and better, then the possibilities of SSOs is greatly reduced. Because you've gone there, you've dealt with the root issue, the grease issue, whatever it was, the backlog that was there, and your crews are able to get around and quite often deal with these things. And blown toilets. Always a topic to discuss, always one of interest, quite often very passionate about people, especially homeowners who are calling to let you know that there was a problem. They don't normally phone and say, hey, by the way, thank you so much for the present, and they're a little irate and a little troubled. Okay, so we're going to talk about that more a little later in the presentation. We're going to go into it in detail and talk about how we can address this issue of blown toilets and how we can make this a much better situation. This is our test rig. I've talked to you about efficiencies and power and this nozzle versus that design and everything else, and it's not pie in the sky or numbers picked out of the air. We actually test and run comparisons and look at all kinds of combinations and different scenarios and different pressures and everything else and try and figure out what's the best design, what's the best route to go. It also gives us a chance to evaluate our products and develop new products, but we're looking at our competitive products as well to understand what they're doing. And sometimes, imitation is the most sincerest form of flattery. If they're doing something right, we want to look at that and go, hey, we should think about that and see what's there. And conversely, I'm sure it's done on our side. So what this ends up being here, if you look at this thing, if you look on the left-hand side where the nozzle is located, that is one of those 98% efficient nozzles, by the way. In here, you've got the hose coming in. You've got the blue box there. That is the flow meter that tells you how many gallons of water are going by. Right above it, there's a little gray handheld indicator. That indicates the impact of the water jets on the plate at the back of that thing. So on the complete right-hand side of the test bench, there is a pressure plate there. And what it's measuring is how much power is delivered to that plate and how is it measured, and go from there. And we're trying to compare apples to apples and see where we're going. So the idea behind this is that we can look at the pressure and bring everything up to an even pressure, bring everything up to an even flow, and then measure the impact on the back. And this will give us our efficiency ratings of the nozzles based on the performance being read out of this device. When I look at this, and I look at that, so this is a Tier 1 nozzle that we ran. We asked everybody who supplied nozzles to supply us with 60-gallon-a-minute nozzles at 2,000 psi. This manufacturer chose a 70-gallon-a-minute. We put it on our test bench. Of course, it read higher than we thought, but we showed the results anyhow because it's quite interesting. Here's a 70 GPM nozzle running. It was sold as 70. It actually measured 69 gallons of water, so it was really, really close. And if you look at the pressure at the nozzle, now this is after 600 feet of hose, started off at 2,000 psi, and at the end of the hose I have 1,400 psi. Okay, so I've lost 600 psi along the way. But the important thing, and I've circled it in red here, is the peak force at the impact plate. This is the power being delivered to that plate. And remember, that's 9 feet, roughly close to 3 meters, not quite 3 meters away. So 9 feet distance is where this impact was happening. And I get a reading off of the impact meter of 13.7 pounds. So the jets of water are hitting that plate and putting 13.7 pounds of pressure against that plate and pushing. Okay? I take this nozzle and I upgrade to a tier 3, and I'm using a competitive nozzle here. It's an ENS Grenade, an extremely popular nozzle, one of ENS's flagship best nozzles, one of their one of their more popular nozzles. They can decide whether it's their best, but it's one of their more popular nozzles. And this one here was rated at 60 gallons a minute. It actually flowed 58 gallons a minute, which again was quite close. My pressure at the end of the hose was 1650 psi. Now I've come up 250 psi from where the 70 gallon was before. So I've lost 12 gallons, but I've gained pressure. And my impact on the end of the plate from 13.7 previously is 75.1 pounds, just by changing the design inside the nozzle and going to something with more efficiencies inside. Now this nozzle itself is probably testing somewhere in the mid-80s range, 84, 85% efficiencies. But if I take the same test bench and I run our 98% efficient nozzle through this same test bench, a 60 gallon a minute nozzle that read 57.4 gallons, 1675 psi at the end of the hose, and I end up with an impact on the plate of 97.2. This is basically same flows, same pressures. The only difference is how efficient the nozzle is to turn things around, and I've gained roughly a 25 or 30% increase in impact and power and thrust and cleaning ability by going to a higher efficiency nozzle. So by using the higher efficiency nozzles, I get more out of what I'm delivering to the end of the hose. If I get more, I can either do more or I can tune the truck down and run less hard. How are we doing time-wise? We're getting there. Okay. Big question of the day, and this is where I'm going to change things up. I've gone over the basics. I presented my theories and everything else. You guys have as much of that as you probably need or want right now. If there's any questions, please send them our way. We'll be glad to respond. In the meantime, let's switch gears a little bit and talk about how we clean pipe. What's the methodology we use to clean pipe? Because I've talked to a million operators, and there are some commonalities, and there are some differences amongst everybody, and everybody has their own way of doing it. I guess just like driving a car, everybody considers themselves an excellent driver, but other people might have a different opinion of that. But anyhow, especially the guy you're following or whatever. But anyhow, so let's look at this. Why are we cleaning pipes the way we are? And what I typically get most of the time on answers is, well, that's the way I was shown. Always done it this way, and things like that. Is there a better way? I'm the kind of a kid, when I was a school-age little guy, I questioned everything. Drove my teachers and my parents nuts. And things haven't changed. My wife still looks at me, shakes her head, and says, you just can't accept things the way they are. But I always question the status quo. I always push. I always want to know why. Is there a better way? What are we doing? So that's kind of what I did with this, and then we ended up finding some really interesting stuff. So if I look at what we discussed previously, we know that pressure loss increases as flow and hose length increase. Remember, the pressure loss we talked about before was per linear foot of hose. So if I have 600 feet of hose on the truck, I'm going to lose 600 times the linear advantage. If I have 800 feet of hose in the truck, it's going to expand, which means I end up with less at the end of the hose. And I've seen scenarios. I was up in Anchorage, Alaska, went up for one purpose and ended up talking to the utility up there, and they said, hey, if you're in town, come and see us. We're having a huge problem. We just can't get things to work. So I went in and had a look at what they're doing. The first thing I noticed were their jetter trucks. They're great trucks. They had 4 or 5 of them. They all had 1,200 feet of hose on them. And I shook my head. I looked at the sides of the hose reel. I said, why so much hose? Oh, we like sometimes to run 2 and 3. Instead of going each manhole, they run 2 or 3 manholes at a time. And they have the odd run where they have these longer runs to go to. I said, okay. I said, 1,200 feet of hose. Do you have a nozzle on your truck that can pull that 1,200 feet of hose off and send it to work? He says, no, we don't. Can't do it. I said, well, then you got 1,200 feet of hose for nothing. I said, let's talk about this. And so I took one of our 98% efficient nozzles. I jetted it based on that specification. And I said, try that and see how it goes. It worked very well. They were quite surprised. We got over 1,000 feet of hose off. We didn't get the 1,200. We got over 1,000 feet of hose off the truck. I then said to the guy, I said, if you're not running the long runs all the time, because the hose on the truck was set up as an 800-footer and a 400-footer, I said, take the 400 off and leave the 800 on and see what happens. And he did that. And he said, holy smoke, it's like a different truck. Because so when you put all that hose on the truck, there's a consequence. There's a price to pay for that. And you've got to think about it. I've seen fellas take 1-inch trucks, drop the size of the hose down to 3/4 inch, and think they're going to use the same nozzles configured the same way going doing the job, and it fails. It fails dramatically. What their goal was, at least in this one case I'm thinking of, they wanted to reduce the water consumption. They wanted to reduce that water they were adding to the sewer system. So what ends up happening is they end up basically handcuffing and shackling the truck, unable to work. So they went back to 1 inch, and I showed them how with the higher efficiency nozzles I can run on lower flows and give them what they want and still provide the power. So FHP is the measurement of available energy. Higher efficiency nozzles deliver more power at lower flow. Lower flow is fuel, maintenance, and downtime, all reduced. Okay, how fast is, stop for a second. What is the proper or appropriate speed to have the nozzle travel in a pipe? That question gets every different answer you can think of in the world. I've had people tell me from slow and steady to let that thing fly to maximum flow, maximum pressure, maximum speed, go, 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 go. The guys are working hard, the truck's working hard, hey, aren't we good? At the end of the day, camera guy goes in the same pipe, looks at it and says, yeah, you got to come back, it's not clean. The guy said, but I did 4 passes, I did so many runs in this thing, I did this, I did that, I did everything as I was supposed to do it. But the trouble isn't with the truck, it isn't with the operator, the trouble's with the nozzle and with the way the nozzle is being applied. So what I'm going to address here is how we run those nozzles. Nozzle technology has changed. Truck technology has changed. But nozzle technology over the last 10 years has changed so much, and the efficiency levels of the nozzles that are being manufactured out there is incredible. And it's turning into a real race to get people the right tools. If the technology of the tools have changed, shouldn't we change the way we work? Okay, back in the day, everything was drilled and sawed, was all with hand power and possibly horse-drawn and who knows whatever was going on. And nowadays we have all these little chargeable batteries that go into drills and saws and makes the job so much different. So the same kind of thing is going on here in effect. We change so much. How do we change things? How do we make things better? And that's what we're going to look at and see what's there. If you take this down to its basic design, I don't care whether it's a $500,000 Jetta truck or a $25,000 trailer or whatever it is, it's just a huge pressure washer. Okay? Your Vactor, Sewer Equipment Company of America, Vacol, whatever brand you're running, okay, it's just a big pressure washer. With attitude, but big pressure washer. And it's got a big industrial vacuum on the back of it. Okay? And if you think about that and put that in that concept, all of a sudden it changes the way you think about how this thing is running. If I have a pressure washer, and I've been off with my 4x4 out in the mud and having a great time on a weekend, and I come back home and I want to tidy this thing up, I take my pressure washer, and if I move that wand back and forth at a high rate of speed, all I end up doing is wetting things down. I really don't do any cleaning. And if you run a nozzle in a pipe and you run it up the pipe at high rate of speed and you bring it back at high rate of speed, you're flying by things so fast it really doesn't have much of a chance to break the stuff off the walls and move it. And that's what generates the problem where you get a fellow who's been out there, whose operator's done 3, 4 runs, and it should all be good. The water's coming back clean. Okay, we're all good. And you go in there with a camera, or you go in with a different style nozzle, and you bring more debris back. And it's like, what? Where'd that come from? Okay, it's because the other tools weren't doing the job properly. So if I think about what I'm talking here is that if I can slow the nozzle down, I can create a better clean. And a better clean means I can do more productivity and everything else and go from there. So job 1 for me is clean pipe. I never, if I can avoid, I never leave a pipe that hasn't been cleaned, that I don't know is done and done properly. Okay? And I always challenge the status quo. There's that 12-year-old kid that's driving his parents and his teacher's nuts there, okay, doing that. So that's what I do, and we go from there. So we're always challenging, and this is where we started looking at things and making some decisions as to what's the right way to go. If I think of the same old, which is the way most operators run their trucks, usually what they do is they take the nozzle, get it down, get it into the pipe, put it in there securely, come to their truck, set the dials where they want to go, ring the pressure up, it's all good, release the nozzle and send it on its way. It flies up the line, and when he gets to the top end, may or may not drop the pressure and start pulling back slowly to clean. I don't know, people that are listening, how many of you are going to say, yeah, that's what I do. And it's not wrong, because that's the way you were taught, that's the way they showed you, that's the way you've always done it, and that's been the accepted norm forever. But if I gave you a shovel and asked you to dig me a hole, would you start from the top and go down, or would you start from the bottom and dig your way out? And 99% of the people out there say, yeah, I start at the top and go down. So my question is, why do you do the reverse when you're cleaning pipe? Why do you shoot the nozzle in and try and pull all that debris back on the way back? Okay. The answers I get when I ask questions, think of nozzles that don't have the power and thrust. Oh man, I got a 500-foot run here, and that's a bit of a hill I got, and if I don't get this thing flying and moving, it's not going to make it. Well, then you got the wrong nozzle on, because you should be able to do that at a normal pace and speed and get things done. You shouldn't have to run that nozzle that high. I get answers from people. I said, hey, you know, I've only got so much water. I got 1,000 gallons of water on my truck, and if I burn 400 on the way up, taking my time, when I come back down, I got to go for water. And, you know, and the boss wants me doing more cleaning and less water. And then the next question that comes up here is, how many times do you run that line? When you're running in this method, you do 2, 3 runs and then call it even? Do you clean until there's no dirt coming back, the water's clean? Or do you do, what do you do? What's the standard? So if I look at the water consumption, because that's one of the big factors folks always throw up and say, no, I need to conserve water. Okay, let's look at water consumption. I'm using 60 gallons a minute truck. I'm running the nozzle at 150 feet a minute in this scenario. So a 300-foot run takes 2 minutes from truck to the upstream manhole. I use 2 minutes to go out. At 60 gallons is 120 gallons. I come back slower, and I've dropped the pressure, which means I've dropped my flow. So I'm coming back. I spend 5 minutes coming back at 40 gallons a minute. So, and then I use a total consumption to go there and back of 320 gallons. The big question is, do I need to make a second pass? If I do, it's 320 gallons every time I go in. Okay? And that's the big question. The total time used to make that pass is 2 out and 5 back, makes for a total of 7 minutes. Another method to clean pipes, and I'm going to go back to this chart in a minute and look at what's going to change here. Step cleaning. And step cleaning is a necessary part of cleaning pipes. If you have a pipe with a heavy amount of debris, think stormwater, think culverts, think things like that are full of rocks and heavy debris and lots of it, then you need to step clean. Because if you don't step clean, what's going to end up happening is you're going to shoot the nozzle in a good distance, and when you start coming back, you're going to pile up so much debris behind the nozzle, you lock it in and you'll just jam it, block up the pipe. So what you need to do is go in, run a distance, let's call it 30, 50 feet, pull back, see how much you have, and then decide, okay, I'm going to keep doing 50-foot segments, I'm going to do 40-foot, I'm going to do 70-foot, whatever, based on how much debris comes back. And you go and pull it out a little bit. Again, I go back to my shovel scenario. When you have a shovel, you don't take all the dirt for your swimming pool out in one big shovel load, you take it out one load at a time. And it's the same thing with this. Go and take a bite, pull it back. Take another bite, pull it back, and keep coming from there. If I look at that, and again, what you end up with this step cleaning process and heavy debris, you end up with a very clean pipe and very little chance of getting stuck. But if you look at the downside to it, you're going to clean that first 50 feet of pipe, it gets cleaned a whole lot. And over a 300-foot run, if you take 50-foot segments, you end up running or cleaning the equivalent of over 1,000 feet of pipe. Over 1,000 feet of pipe that you've cleaned and you've gotten done, congratulations, the job is done. It's a good job, the pipe is clean, but it's cost you 3.5 times what it should have to get that job done. But at the end of the day, pipe is clean, and as a supervisor or utility manager, I'm happy, pipes are clean. Now, if I can just find a way to do this easier, a little less expensive. Tier 3 nozzles, you go back to what I've been talking about. Tier 3 nozzles deliver the higher efficiencies. They can run on lower flows, little less pressure, and still provide you with excellent cleaning power to do everything you want it to do. The other advantage of Tier 3s, of course, is if you really want to put the truck into overdrive and deliver all that power, it will deliver power back and move heavy, heavy, heavy debris out of the lines. So what I want to talk to you about is instead of sending that nozzle up the line at a high rate of speed, I want you to send it out at a slower pace. I want you to walk it up the line and not run it up the line. If you walk it up the line, what you end up doing is allowing that nozzle to clean and pull the debris off the wall of the pipe on the way up. The flow of the water that you have in the pipe that you've added, that extra 40, 50, whatever gallons, that flow of water that you're providing is enough to carry that debris back towards the truck. Okay? So if you go out slow, let's even call it same pressures and everything else as you had before, but go out slow, you will clean much, much better. And if you clean much better, then you can typically get this done in one pass. Upstream cleaning will remove all the debris off the walls of the pipe and throw it into the water stream. The water stream will carry it as the system is designed. Remember, it's a gravity-fed system. The water stream will carry this debris down towards the truck. Anything light, paper, grease, organic matters, will all find its way to the truck. Anything heavier, sand, rocks, things like that, will tend to settle out of the water stream at a distance from the nozzle, which is fine because when we come back down, we'll collect this stuff. So going out, I do my major cleaning on the way out, and on the way back, what I typically do is I drop the pressure down quite low to 600-700 psi and collect all that debris, the rocks and stuff on the way out. Because remember, the pipe is now cleaned, all the soft organic material, all the grease, all the paper is all gone. What I'm moving along now is rocks, sand, and pebbles. And in a clean pipe, it's like rolling a ball on a piece of asphalt or a gravel road. It'll roll farther on the asphalt than it's going to roll on a gravel road. So again, upstream is cleaning once, downstream is second pass. So from that one pass of the nozzle, one in and out, I'm actually cleaning in two directions. And by getting that done, I can clean this pipe in 99+% of the time. I can clean sewer sanitary pipe in one pass. So instead of having to go back in a second and a third time, hopefully we have the job done right and go from there, it all works. I have a scenario, I was teaching this exact class to the city of Calgary, and I had one of the operators in the room was reluctant to accept that this made sense. So I went out with him after the class was finished and with his truck, and I had him allow me, because again it's the city's equipment and he's a city employee, he allowed me to set the truck up, the parameters of the truck up, and then I told him, I said, just run it. And he did, and when he first tried it, he said, this isn't going to work. I said, Curtis, give me the time to show you what this is about. And he did, and then he was shocked. It worked very well. I saw him months later, and he looked me straight in the eye. He says, you saved my life. He says, you made my job so much easier, and I am now the highest productive employee the company has. He's consistently the #1 in meters done, and he gets, I use the term zero, his terminology, 0 callbacks. He says, I used to get 3 and 4 a week. The camera guy would go, whoa, Curtis, got to come back to this one. Okay? Now he gets nothing, because once he's finished with the line, it's clean. So again, slow the nozzle down, allow the nozzle to clean on the way out, and then clean again on the way back. Big advantage in cleaning and productivity. We're also going to talk about the other advantages this is going to bring us when we talk about blown toilets. So I've looked at before, you see on the left-hand side of the screen, that's my same old, same old. That's the 320 gallons for a 7-minute pass, and probably need a second, maybe even a third pass. If I do the same thing but in my way, okay, I hate the term my way, in the newer way, okay, I take 5 minutes going out, not 2. But I'm only burning 40 gallons a minute because I've got a higher efficiency nozzle and I can use less water. And I can go out at 40 gallons a minute and burn 200 gallons on the way out. And then when I'm up there, I drop the pressure down and I come back at 30 gallons a minute, and again at 5 minutes. So I'm in the pipe for a total of 10 as compared to 7. I'm burning 350 gallons of water versus 320, and I'm in and out in one pass. That means I can go on to the next one and the next one. Might even get a fourth, depending on the truck you have, out of this system. Whereas with the other truck, you've done 2 or 3 passes in this one line, time to go get water. So your productivity, your meters done in a day, the work demand on the truck, heck, the work demand on the employees, the guys running the truck. Okay? It's actually a pretty cool job. It's not a bad job at all. You're outdoors, if you like that stuff. You're in public, if you like that stuff, and go from there. But what's unpleasant is the dirtiness of the job. And people say, you work in a sewer. Well, I don't. I work cleaning sewers, but I don't get in the sewer, right? But some days when you come out of that job, you look like you've been in the sewer. I've seen guys covered head to toe and not looking pretty. So the whole idea here is if you'll accept the fact that what I'm showing you and think about the numbers I'm putting out, for a lot less time, water, fuel, I can clean a 300-foot section of pipe like that. More productivity, fewer blown toilets, and that's coming up next. Okay? We're going to look at the hose. I mean, hose damage, every time that hose goes out, it runs the risk of being damaged. It's going out and coming back, and going out and coming back, and next thing you know, there's a tear in the hose. Oh, geez, okay, I'll put some tape on it, and let's get back at her and go from there. I use the term tape with safety in mind. The hose is retrieved. If I go out and I clean on the way up, when I bring the hose back, I bring it back through what is in essence a clean pipe. So all the grease, all the organic matter, all this stuff in there that's unpleasant has already been cleaned and removed. So when the hose comes back to the truck following this procedure, it comes back to the truck cleaner. It's not dripping. There's not things hanging off of it. It's stored on the truck cleaner. The operators themselves end up being cleaner. The environment is healthier, and the main reason why the environment is healthier, especially in these days of COVID and protections and masks, and everybody's worried about sewers and what's actually down there, how much stuff down there do I really want to, do I want to know about what's down there, or do I just want to close my eyes and do my job? But when you're bringing the nozzle back to the truck, if you're running a nozzle that's less efficient, one that opens the spray and opens that fan up that spray, and if you bring it back to the truck under high pressure, you get a mist that comes out. Quite often it's pretty strong mist, sometimes it's very little bit mist, but get a heavy mist coming out. And I've had scenarios where I've had to take off my glasses and clean them afterwards because that just come out and enveloped everybody standing by the manhole, and the stuff coming off wasn't nice stuff. I needed to go clean and shower afterwards and all that stuff. But the idea is if I bring the nozzle back through the cleaner pipe and I have lower PSI, lower flows, and I'm just collecting the rocks on the way back, number one, I'll have a whole lot less mist, and any mist that's there is just going to be water. It's not going to be full of contaminants. So from a health point of view, that does make a huge thing. And the last biggest advantage of this is if you think about it, and I don't know anybody, I've had it happen to me, and I've heard stories of all kinds of things, scenarios happening, nozzles getting turned around when they're in the pipe. And what happens is the nozzle go down the line and either deflect against something and get turned around and come back, or deflect and go up a service. Or the one I'm thinking of in my head, the nozzle went down to the other end, the manhole dead-ended, it slammed into the wall, ricocheted back, and come straight back down the pipe. You know, the 1 in a million shot you'd never do again, but this one happened, and it came straight down the pipe. And I was standing beside the truck operator, and I'm hearing the truck thing go out, and I'm listening to the noise, and making a certain noise going out. All of a sudden, it stops taking hose, and the noise changes. Like the change is different. It's not that same aggressive noise. Now it's more subdued, and I'm not taking any more hose. Because what's happened is the nozzles come back into the pipe, and it's now traveling towards the truck or towards me with no control. Okay, because if I have a hose reel and it's going out, I just stop paying hose and it stops. But now, as long as I provide water, that thing's coming back at me. So what happened in this case is it came out. I talked to I said the operator. I said, shut off your truck. He looked at me and said, what? And he didn't even get the T out of what. He got what? And that nozzle came out of the ground and went straight between the two of us. Straight up. And it probably went 25, 30 feet in the air. Okay, he saw that happen. We're in traffic out on a busy street. He saw that happen. As he's stepping back, he hits the E-stop button. Poof, the truck shuts down. The hose is in the air, it dies. It droops over a power line. So now I've got water, truck, power line, sewer, traffic. I don't know which way to turn. Okay, all I want is out. I want out of here. I want out of here now. So by slowing down the nozzle and sending it up the line, allowing the nozzle to clean on the way up, the opportunity to hit something, rebound, and come back is greatly reduced. If I'm going in at 150 feet a minute and it hits something, I've got a good head of speed, boom, and it comes back. If I'm going in at a more sedate walking speed, I bump into something, it's just going to hit and stop. So again, it can be safer from that aspect as well. Now we're going to get into blown toilets. And my mistake is I gave the people at EOCP here a PDF version, and if it had been the PowerPoint presentation, I could have done things. But we'll get through it anyhow. What causes blown toilets? And at this point, I usually ask the crowd, okay, guys, give me some thoughts. You guys, you got 15 years in the saddle. You're new on the job here and there. What do you think causes blown toilets? And I'll hear all kinds of things come back, from, too much pressure, to flat lines, to plumbing issues in the home, to there's all kinds of reasons why toilets will blow. But the major reason, the most common reason why people experience blown toilets is simply air pressure. And if you think about for a second that nozzle, and we'll think about a common nozzle with all the jets rearward, whatever angle they're at, that nozzle is sending water this way. If I put that inside of a pipe, it acts like a venturi and draws air ahead of the nozzle. And operators who've done this, and most operators have had this experience, they've set the nozzle in the line, started on its way, and they'll send a guy up to pull the lid, watch for the nozzle to show up, he signals to his buddy and puts the lid back in place. Well, when he shows up there and that nozzle's on its way down the line, he's got to put his back into lifting that cover because the vacuum is sucking it down hard. Okay? That's how much air moves. When I do demonstrations, like you saw that clear tube with the impact plate before, when I do demonstrations with that, I have folks come up and put their hand in front of the nozzle just to show how much is there. And they're all amazed at just how much air there is. It moves air at an incredible rate of speed. And if you think about it, what's causing this thing to happen is, let's take an 8-inch pipe, which is very common in industry. An 8-inch pipe, as the nozzle's coming back and is drawing air, creating a vacuum in front, it's drawing the air across the nozzle. So the 8-inch column of air is coming down and traveling to the nozzle. As the air travels over the nozzle, behind the nozzle I have a 1-inch hose, and I have an additional amount of water I've added to the system. So I've taken space in my 8-inch pipe with the hose and the water. So my 8-inch pipe, due to the water in the hose, becomes a 7-inch pipe. And somewhere behind that nozzle, remember I'm cleaning now in the same old manner. Somewhere behind that nozzle is a field of debris that I'm trying to get out of the pipe. And that can be a big field, a small field, it can be all kinds of things. But that field of debris takes my 7-inch pipe, remember 8 down to 7, and then it goes down to a 6 or a 5 or heaven forbid a 4. And I'm trying to push an 8-inch column of air moving at a great rate of speed through a 5 or a 4-inch hole. What I end up doing is compressing the air between the nozzle and the debris field. And as that debris field goes by Mrs. Kowalski's house, she gets a little surprise. Okay, because the air goes up that surface because it's restricted behind the nozzle, but now I've delivered a 4-inch service line straight into the house. If the house is properly vented and nobody has messed around with the venting and everything else, typically it shoots to atmosphere. Or if you take off the cleanouts in the yard, you'll see it come out there. And you'll see a fair amount of air come out of there. But if for some reason the vents are blocked, somebody's done some renovations and didn't hook things back up right, or any other scenario, if there's not enough room to blow off that pressure up into the atmosphere, then you will end up with a pressure inside the house, and that toilet will pop, will blow. And sometimes it's a little gurgle, gurgle, bubble, bubble, and sometimes it's things are hanging off the ceiling. Okay? Homeowners tend to get upset. Quite upset. I've had everything from people coming out swinging baseball bats almost at us to scenarios where folks have come out. One guy came out laughing quite a bit. He came out and started chatting with us, and he was taking an aggressive stance and pointing his finger, but his big smile on his face, because his wife was in the window of the house watching him. And I guess she was sitting on the toilet, and she got a little bit of a shock. And she got after him, and he came outside to talk to us, but he thought it was a little more comical than she did. But again, I guess when you're sitting on the toilet, that makes a change. But the toilet The main reason toilets are blown, and we're going to talk 80–85% of the time, the main reason toilets are blown is this column of air, or this volume of air that's moving in and out, and it has to go somewhere. You know, and if you just compress that, even a few pounds of pressure behind the nozzle is enough to send a surge up the line into the home. And again, the homeowner gets upset. So who's to blame? Ask the homeowner, they'll tell you, right? It's your fault. You're the operator, you're the foreman, you're the city, you're the mayor, you're the whatever. It's your fault. But the city needs to clean these pipes. Okay, it's got to happen. Because if you don't, you think having a little in your bathroom is something. Wait till it starts backing up big time or starts flowing down the streets. So the city has a right and a responsibility to clean these pipes and to get it done on a regular basis. And especially if there's an issue where there's sewage back up into the homes, you need to be able to show that the lines were cleaned on a regular basis, and the last time they were cleaned and inspected was this date, and the incident happened 6 weeks later, and those pipes were cleaned at that time. So we did due diligence to make the job. If you haven't cleaned it in 4 years and there's a backup, you might have a hard time winning that case. Okay. What can we do to reduce the chances of blowing toilets? And often I'll have operators, oh, I just drop the pressure way, way, way down and just kind of get that nozzle, go up the line, and then get in, get out, and get out of here. Okay, so he's managed to clean the line, quote unquote, with minimal pressure, and he's managed to not get the homeowner irate. So far it's success, until you go look at the pipe. And you realize he hasn't cleaned the pipe. He's moved debris, some of it's gone, but it's far from clean. So that means, A, you're already started on your next cleaning cycle, or your next blockage, or the next whatever's coming down the road, or you need to go in with a little more authority. Or if you're going to run that way, you may need to run 2, 3, or 4 passes, and every time you go in, you run the chance of having that homeowner come out and say, hey, you just did it again. Okay, so the question now is how do we go about doing this? Lowering flow and pressure is a good idea. It works. I preach it, I teach it, it works. But use the right nozzle. If you have a nozzle that's producing 30% efficiencies or 60% efficiencies, and you turn the truck all the way down to just about nothing, you won't get any cleaning power out of that nozzle. And if you have a higher efficiency nozzle that can do that job, then you can send it in there at the same flows and pressures, reducing your air draw and all those things we talked about, and give you the clean pipe you need, and pull the line up as you pull up the line as much as you need it to go. So if you have an issue with blowing toilets, there are things you can do, and it doesn't require a huge change in business, it doesn't require a huge investment, and go from there. That being said, nozzle manufacturers, there's one in the front of the room here, nozzle manufacturers do build tools specifically designed to reduce the opportunity to blow toilets. This is what we offer. We call it the equalizer nozzle, and it's designed, let's look at the terminology, virtually eliminate. Okay? And the reason we use the term virtually is because we don't know every connection out there. We don't know every scenario in North America, what's going on. But if the issue is an airflow issue, as in most cases, this nozzle works extremely well. The downside of that nozzle, it's probably north of $5,000 Canadian. And for a lot of people, that's just a little too much money to spend on running on this. We can, using a higher efficiency Tier 3 nozzle, I go back a slide, to a regular Tier 3 nozzle, a decent quality Tier 3 nozzle, and I can show you how to clean pipes and do that. I had the City of Ottawa, I'm going to do this last thing here. So I can reduce flow and pressure, which means that I have less draw of air in the nozzle, less compression of air. It helps, but I may not get the pipe clean. If I buy the fancy tool, okay, it'll do the job, but number one, that nozzle has got 18 orifices in it. It burns water like nobody's business. But it does the job it needs to do. So if you have a tough problem, there's your answer. But if you just change the way you clean pipe, tool and methodology, you can greatly reduce. The third item on this slide here talks about remove the material from behind the nozzle. So you remember I talked about the airflow in front of the nozzle. It crosses over the hose, the water, taking up some space, and behind is that debris field. If I use the method I talked to you about before, and clean on the way up, and allow that debris to fall into the water stream, hit the water stream, and carry out, when I come back, that debris field is not there. And if the debris is not there, the restriction in the pipe is gone, which means that the air that I'm bringing in and moving along will have a place to go. City of Ottawa, 2 years ago now, it's 2 years ago almost to the day, they phoned me up actually in May of that year, and in September I did the training. They phoned me up and they had a huge problem. To put it bluntly, the fellow who phoned me up says, we have a problem and I don't know how to fix it and I need help. I said, well, what's your problem? He explained to me, and I said, okay. The city council had stopped him and his whole department from going into certain parts of town because those areas were prone to blowing toilets, and he wasn't allowed to go and clean these pipes. But he knows as well as everybody else, I got to get in and do them. I just got to find a better way. But the city said, no more until you can fix the problem. Okay? So what I did is I discussed with them what the issues were, threw a few ideas his way, and his comment to me at that point in time, I think it was May of the year, he said, when can you come? I said, well, when do you want me there? He said, well, summer's coming, so let's not do it now. Let's wait until summer holidays are over, and then we'll get into this. And in September, I went and I did 2 days, half the crew one day, half the crew the other day, classroom like we're doing now, demonstration outside on that clear tube assembly, and then we went and ran lines. So 2 days in classroom with the demonstrations, and then one day, the Wednesday of the day, we went out and we actually ran lines. So for 2 days, I taught the folks exactly what I've talked about here, and then I showed them in the tube assembly what's going on. You can see it in the picture there. We're running the tube assembly. And then we went out. The big test was, okay, we'll take you to one of the bad areas of town. We'll take you to one of the bad areas of town, and we'll let you show us that this actually works. We ran there from 7:30 in the morning till 11:30 in the morning in a bad neighborhood. And the only contact we had with a citizen was somebody walking his dog who said, huh, what are you guys up to? Okay? 4 straight hours, not one incident, where before every second house was going. So that changed everything for them. In this report, they actually sent me a few months later, in their Public Works Environmental Services Division News. That's what PWESD is. And they came to me and sent this report. They show where they've reduced by 88% the opportunities or the times they blow toilets. So the incidence of blowing toilets greatly reduced. I said before 80 to 85% is air. They've shown it's in their case was 88. But what I'm saying through to you is this works. So not only by changing the way by buying the better quality nozzles and having them jetted correctly, but by changing the way that we use the nozzle and clean the pipe, I can clean the pipe better, I can use a lot less fuel, water, time, etc., and I can reduce your incidence of blowing toilet, all with just that one change. Angles of flow on the back of nozzles. We did a lot of talk about inside the nozzle, how the water's turned. We've talked about all kinds of things. What I want to talk about here real quickly is on the nozzles on the back end. You can get wide angle nozzles, you can get a very tight pattern behind and go from there. I want you to understand, a very tight pattern behind the nozzle means that you've got a lot of thrust and power, not a lot of cleaning capacity. It doesn't go to the walls of the pipe. If you have a wide angle, your cleaning to the walls of the pipe is tremendous, but your thrusting might be less, maybe not enough to get the job done. There are nozzles in the marketplace. We make them, pretty much everybody makes them, dual angled. Like I'm thinking of one nozzle is 15 and 25 degrees. 15 degrees to propel it, 25 degrees to scour and clean. And that nozzle does an excellent job. That's one of the nozzles the City of Ottawa bought and put into practice, go from there. One of the nozzles that my local dealer here in British Columbia sells a lot of because it's priced very nicely. It's more money than most folks want to spend, but it's not as bad as some. And the other thing is that it does the job very lean and mean. So we can go from there. So wider angle, more power and more cleaning. Tighter angle, more thrust and power. The tighter the angle behind, the more air the nozzle draws. So if you're having issues blowing toilets, a bit of a wider angle will relieve some of that issue. What's the time right now, folks? 11:40. So we got about 15, 20 minutes. Okay, when it's time for questions, I will invite anybody who's listening, if you have questions, send them in. And when it's time for questions to go, I still have some stuff to go over, but this is to fill the time, so we're good. Okay. What I want to talk about is using the right tool for the wrong job, or the wrong tool for the right job, or vice versa. In other words, the right tool, right job works. Okay, here the fella's obviously picked up a hammer, fancy hammer, but it's a hammer, and he's using it appropriately, maybe not. And then this guy, of course, he's got the right tools, but maybe not enough of them. You'd be there for a while blowing that tire up. So some of the things you want to look at, I've been talking to you guys about jetting your nozzles and dropping your flows and all that stuff, but there does come a time in the operation of your jetter truck and cleaning your pipes and your sewer systems and stuff when you actually need the heavier flow. And then, of course, then you decide, well, what do I do? Do I buy a nozzle with a heavy flow? Do I buy a nozzle with a light flow? Do I buy one of each? And the nozzle salesman says, yes, please, thank you very much. Or how do I do this? Or do I change jets in nozzles and let my guys mess around with jetting, which I don't recommend because it usually ends up in a mess. Lost inserts and things going in the wrong spot and everything else. But the device on the left-hand side, we call a turbo adapter, and what it does, it threads into the back of the nozzle, and it adds, in this case, 3 extra jets and roughly about 15 gallons of flow. So a nozzle jetted at 50 gallons a minute will all of a sudden become a 65 gallon a minute nozzle with the extra water and flow to help carry material and debris away. It's just an easy way of fixing a problem that came up once we started going lean and mean on nozzles. This nozzle here, and there are videos in this presentation, but we won't get to them. This nozzle is designed for breaking hard materials. Think concrete, think calcium deposits, and everything else inside a pipe. It'll start bouncing. For a 1-inch hose, this thing weighs about 6.5 to 7 pounds. And when it'll start bouncing it, I can get it bouncing a foot off the ground. Necessarily, if you're cleaning clay pipes, this is not the tool to use because 7-pound hammer jumping up and down a foot in the pipe, your clay pipe is not going to survive very well. But on steel, ductile iron, PVC, HDPE, concrete, all that stuff, it works extraordinarily well. That's video of the nozzle. We're not going to see it run. Large diameter storm waters and everything else, these flat bottom cleaners you see on the left-hand side are very, very good at doing that. If need be, and I've worked in pipe as big as 10 feet. I know of a fella, actually I've been inside of a 17-foot pipe, but I've worked inside of a 10-foot pipe, 90% blocked with stones, gravel, rocks, brush, everything else in it. And I set up a set of twins and used an 80-gallon-a-minute truck, and we cleaned that pipe and got the job done. A lot of contractors and a lot of vendors had all showed up to try and deal with this, and they couldn't get the job done. So we did it this way with the twins. This was a video of, I was up in Anchorage, Alaska, and they had a very hard-packed driveway. It's gravel or dirt, been driven over for years, and they were wondering just how effective the floor cleaners were. We ran a video, and they actually run this thing in slow-mo, and you should see this thing flinging mud and dirt. It's pretty amazing. So if you ask for a copy of the presentation, maybe what I'd like to do is give the EOCP a copy of the PowerPoint as opposed to the PDF, which will play the videos and you can see these things going on as well. This nozzle, as surprising as it might sound, is known as the OMG nozzle. We called it that because the first time I used it in a pipe, somebody looked at me and said, "Oh my God, has that thing ever moved dirt?" And yeah, it did. It moved big time. So CMP is a corrugated metal pipe, stormwater, the culverts, that kind of stuff is what this is designed for. It is a debris-moving fool, and it will penetrate and dig into piles of debris and move them straight back without disturbing. One of the problems with corrugated metal pipe is that the bottom of the pipe tends to rust out. And if you go in with like the previous nozzles, a floor cleaner, all the jets are angled down to the floor, which means that if there's a hole there, it's going to start taking the fill and the gravel away from the pipe. This nozzle, the jets are straight out the back, almost 100% straight out the back. And what that gives you is takes the debris that's in the pipe and moves it out and doesn't allow the nozzle to dig holes and things like that. So it works extraordinarily well. Again, here's a video that I ran. I was down in Las Vegas at our dealers down there, and they had demo days, and I ran this nozzle. We put the bales of hay behind and ran this nozzle, and you can't see it, but if you look at the pipe, you can see there's hinges and latches on the pipe. We dropped inside of there about the equivalent of about 2.5 yards of sand, gravel, rocks, put a bit of water into it, a bit of mud, put a bit of water and mud into it, and we let it set for a few days, and then we ran the nozzle in, and it moved that debris out in about 20 seconds. It was gone. I'm getting a signal that we're running out of time, so I guess the question is, if there's any questions, now would be an appropriate time to send them in. Happy to answer any and all. If not, I'll just continue and go from there. So James, if you get anything come up, let me know. Oh, we have one. Okay, thank you. Thank you, Tony. Any information on root cutting? It's funny, the next slide I was getting to was about root cutters. So Tony, yes, absolutely. We have a range of root cutters that runs from 2-inch all the way through to 48. One of the cutters we have will run 6-inch through 48-inch and actually go beyond. High speed of high rotation, high torque cutters that do an excellent job. My information will be available, I believe, through the EOCP. If you wanted to reach out to me, I'd be happy to discuss your needs and then get back to you and let you know exactly what you should be using and how that could apply to you. So we had the root cutter before. This is that big one I told you about, runs 6-inch through 48s. This would be a video showing this thing cutting a 6-inch taproot coming down into a 24-inch concrete pipe, and it goes through it. You know, it works at it, but it takes it right out very well. Next video was a concrete lined pipe that came out of an exit from or the outflow from a concrete plant, and how to get that stuff out of there. And again, the chain flail went in there and did a good job on it. When it comes to taking roots and root cutting, sometimes we don't need to get as drastic on that as a mechanical tool. There are some very good tools on the marketplace. They're called controlled rotation nozzles. Warthog is a brand name that's very much seen around the industry. We have our offering is on the left-hand side, but these are both using water jets instead of chains. But the advantage of these is the mechanics inside the nozzles, and they both do it differently, but they slow the rotation of the head down, which means that those jets of water not only are angled to be effective to cut the roots, but at the speed they're turning, they spend a lot of time working the root and working the root and working the root, and you can actually cut through some pretty impressive roots. Next video shows actually my hand, and you can see the root mass that we cut. It measured about 1.25 inches, 1.5 inches in diameter, and we cut that with that tool we just saw. So again, when it comes to root cutting, I like to flush with a regular nozzle, a high efficiency nozzle, bring back as much sand, rocks, debris, and roots that it can bring back. Then I go in with a tool like we just saw, the controlled rotations, and if that can do the job, great. And if worse comes to worse, we get a big root mass like we saw before, that big 6-inch trunk coming in, then I have to go in with a tool to cut it out, and that becomes the chain flail and the root cutters. Okay, this is a video we had of that test, and you would have seen a piece of 2x2 be introduced into the tube, and you would see in 60 seconds it just about cut the 2x2 in half. So again, it's just a question of how effective these can be in doing things like mineral deposits, grease, roots, and all the stuff we find inside our lines. This here is a camera nozzle, so it's designed to be able to clean pipe and camera the line at the same time. So for smaller municipalities that don't have a dedicated camera truck, or for people who have, I don't know, 4 or 5 jetters and 1 or 2 camera trucks, and the camera trucks are so far behind the jetters they'll never catch up, this tool will allow you to assess the quality of the pipe while cleaning, so there's no extra steps required. It'll allow you to go down, clean the lines, capture the video. You see the video or the pipe in its condition before the cleaning happens and immediately after the cleaning. So number 1, you show up and you can see how bad it was, and number 2, you can look at it and say, yeah, I got it, and it's done. Again, all these tools, everything we've talked about, it's all available for demonstration should it become required. Happy to do it. A couple more questions came up. Mr. Peter, use a pipe cleaner. Have you any disconnected pipe from a... You got an asbestos cement line 6-inch, and your issue is disconnected pipe from a bell, so they're coming apart. I'm not clear whether that's happening during the cleaning process or whether the things have settled over time and you open that joint up. But yes, have many tools that can help in that scenario. There's a lot of questions I have yet to answer. So Peter, I'd be happy to, again, contact me, let me know. On the front hose reel, the colors. Yeah, okay, that's a very good question. It's not related to nozzles, but I can't answer that for you. The hoses are the outside coating will reflect the pressure rating of the hose. Blue is typically 2,500 psi. Orange will be 3,000. Green will take you to 4, if I remember correctly, and things like that. So that's important. But the other very important thing is the color of the inside tube. If you have to rejoin an end of a hose, or you need to cut it and repair a hose, put a hose mender on, it's very important that you match the color on the coupling that you're using and the crimping tool you're using to the interior color of the hose to get the right diameters. If you don't do that, you run the risk of having that joint open up and come apart. Could be a problem for safety, definitely be a problem for performance and everything else. Okay, that being said, there's the jetter camera we talked about. There's a video we tried to run. Grease and odor control, we're not going to go there. They're going to go right through that. Come on. And there we go. Quick review of everything. Clean your wastewater storm lines better is one of the things I promised you in the beginning. I hope I've shown you a way to do that. Savings on fuel. I know I can do that for you. Reduce man-machine hours, wear and tear on your equipment, water, everything else is all there. I invite anybody who's interested to reach out, contact me directly through the EOCP, or if you can contact me directly, there's my information there. Happy to work with you and to find a way to resolve some issues. Let me see, how would you recommend cleaning low pressure collection system that have limited access points and small diameter pipes, 2 inches? I'm assuming you're running a 1/4 inch hose or a 3/8 inch hose, a jetter, and you're at Aquatech, I know where you are. Gabriel, yeah, again, a lot of answers, a lot of things we can do. The only thing that I would suggest again is reach out, give me a call or an email and ask me quite simply how can we go about doing this and what can we do. Big fan of doing demonstrations, big fans of putting product in your hands and letting the product prove itself for the jobs in question. So if there's anything that you're interested in and we're going to recommend to you, very, very ready to put it in on a trial basis, have you to evaluate it for a couple of days. Is it doing the job? Yes and thank you. And if it's not, then send it back. Gabriel, I hope that answered your question, but if it doesn't, again, I'm available. Reach out to me. And I think we're done. James, are you all done? The questions? Okay. Well, folks, thank you so much for allowing me to come today and speak to you, and hopefully that this has been of some use to you. If there's anything at all that I can help with, I'm available. So, thank you.
Thank you so much, Kenneth. We really appreciate that, and I just learned so much. My main takeaways were pressure cleans and flow moves, and it's all about, and it's all really about the nozzle and the pipe cleaning. It's the efficiency, conserving energy, money, and time, as well as sanitation and staying clean while doing a good, fast job.
Perfect.
And,
well, thank you.
So thank you so much. Thank you for presenting on behalf of the
Thank you so much.
EOCP.